Good afternoon, everybody. My name is Malamar Friboll, and I'm a PhD student. I work at the University of Palermo. And my presentation topic today is modeling the electromechanical impedance method for the prediction of the mechanical behavior of dental implant stability. It may be considered quite relevant for those who work with non-destructive techniques and also with dental implant stability assessment. And this study was conducted at the University of Pittsburgh under the supervision of Dr. Rizzo. I divided my presentation into 6 main parts. I'll be starting with the research motivation. I will move on to the research objective. Point 3 deals with the numerical prediction. And after that, the experimental validation of the problem. Actually, this part is not included in the paper, but included in my presentation for the sake of completeness. And at the end, the results and time for questions. We first need to identify the clinical problem and give some definition for those who don't know. A dental implant is an artificial device that is placed in contact to the jawbone in order to restore one or more missing teeth. And our natural system is composed by the natural crown and the natural root. The artificial corresponding system is composed by the dental implant, the abutment, and then the artificial crown. The most common clinically used implant therapy is based on the 2-stage protocol advanced by Brainmark, and at first stage consists of the surgical insertion of the implant into the jawbone. And after a healing period, second stage is performed by screwing the abutment into the implant and then by connecting the artificial crown. And this healing time is strictly necessary to make bone remodeling and reproduction occurs. And this time ranges from 3 to 6 months depending on several factors such as the type of the implant or type of the bone or the patient. To understand what implant stability means, we have to distinguish 2 kinds of stability. Primary stability is obtained as an outcome of the mechanical interlock of the implant into the bone, and secondary stability is a long-term process where bone remodeling occurs. So what is clinically demanded is a reliable, non-invasive method able to assess the degree of disintegration, also the implant stability. And this method has to do a local measurement of the biomechanical properties around the implant. And imaging techniques like radiography or computer tomography and also biomechanical techniques have been developed. And the most common clinically used biomechanical techniques are the period test and the hostel, based on the resonance frequency analysis, just to be mentioned. And I want to say that biomechanical techniques are more advantageous in terms of cost and also absence of radiations. So let's move on our goal, that is to apply the electromechanical impedance technique to assess the degree of disintegration. Actually, this method is generally used in the structural health monitoring of aerospace and mechanical engineering, and its application in biomechanical engineering is rare. The method consists of bonding one piezoelectric transducer to a house structure to be monitored. And when an electric voltage is applied to a transducer, it causes structural excitation to the area close to the transducer. So we basically want to measure the mechanical impedance of the host structure by reading the electrical properties of the transducer, in particular the electrical admittance. The electrical admittance is defined as the ratio of the current flowing through this transducer divided by the external voltage applied. And this is a complex quantity that is composed by a real term that is known as conductance and the imaginary term known as susceptance. It has been proved in literature that the real part of the admittance is more sensitive to any change in the structure. So as you can see in this plot, this is a plot of the conductance signature as a function of the actuation frequency for a piezoelectric transducer bonded to a thin aluminum beam. And the solid and the dashed lines represent the undamaged and damaged case when a hole was created into the beam. And so we can see that the conductance is sensitive to the change in the structure. And these peaks and valleys actually correspond to the structural modes of vibration of the of structure. So let's move on our numerical study. Before applying our method to our purpose, we start doing some simulation using the finite element software ANSYS. And in this slide, you can see the simulation represented by the free piezoelectric transducer. That means that was considered completely unbounded. And the piezoelectric transducer that you can see here, it was 2 per 2 millimeter per 0.2 millimeter. And we perform a coupled field analysis using a solid 5 element, that is an element basically that has 4 degrees of freedom, the 3 special displacement, and then the voltage. And the degree of freedom of the voltage was coupled on the top and on the bottom surface of the element just to simulate the electrocodes. And an harmonic voltage was applied to the top surface of the piezoelectric, where V0 was 1 volt, and then we apply 0 volt to the bottom surface just to simulate the ground. And then we obtain basically the conductance, or like the real part of the electrical admittance, just calculating the derivative of the charge. And this plot, the red plot, represents the numerical plot, where we can see that the main resonant peak was at around 900 kilohertz. And I decided to overlap also the experimental plot to see that there were a very good agreement also in the close-up view, but I will explain in a while how we obtained that. And the second simulation represents the free superstructure. I will refer to the superstructure as the system composed by the piezoelectric transducer bonded to the abutment and then connected to the implant. And we can see that we have also, this is the conductance as a function of the actuation frequency. The main resonant peak of the piezoelectric transducer was around 900 kilohertz, but then we can see that there were some new peaks that represents the whole structure resonant peaks. And this is more evident in the close-up view. To conclude this numerical study, we did a three-dimensional simulation by considering our superstructure inserted in a finite size block that was simulating the bond. And to simulate the osseointegration process, we assumed the existence of an interfacial tissue. This is this part green, represents this interfacial tissue that was 1.5 millimeter, where the Young modulus was considered variable from 10% to the 100% of the Young modulus of the bond. And these two extreme cases represent the lack of osseointegration, the perfect osseointegration. And as you can see in this main plot, there's no dramatic change. But then if we see in the close-up view, we can see that there is some change in the behavior of the peak. And we try to extract some feature to understand if there were some sensitiveness of the method to the different Young modulus. And we choose two resonant peaks, one the highest frequency peak of the piezoelectric transducer and one lower frequency peak. And we saw that there was an increase in the amplitude and also an increase, a shift over RF frequencies. Then we did the experimental validation of the problem, and just to be mentioned, usually the impedance is measured by using some expensive device like impedance analyzer or LCM meter, but in this study we used a very low-cost system that was constituted by electrical circuit that was coupled to an IDAT acquisition system driven by a LabVIEW software. And basically the measurement of the impedance was based on the frequency response function that was calculated by means of the discrete Fourier transform of the input signal and the output signal. And we developed this expression by considering that the input signal was a chirp signal, and then we expressed the output signal as a function of the input one, and we obtained an expression where the only unknown was the impedance of the transducer, and the frequency response function was the measured one. So we did in this slide is described the setup. We basically choose this PZT patch 2 per 2 millimeter per 0.2 millimeter, and we bonded it to the abutment, and then we connected to the implant to realize the superstructure. And then we insert the superstructure into a bovine bone sample, and to secure the superstructure into the bone, we use a pulp canal thinner that is a dental cement paste in order to measure the impedance while this paste was curing. And we measure the impedance along 12 hours every 15 minutes, taking 50 measurements. And in this slide you can see that there is the conductance as a function of the actuation frequency at the time, for the free superstructure, the black line, and at the time of the insertion, that means 0 hour, and after 1 hour, and after 12 hours. You can see that the main change is after the insertion, and this was somehow expected because the damping changed promptly. And if we focus always in one peak, that is the yellow underlined there, we can see that there is a certain trend over high frequency, a certain shift over high frequency. And in these graphs you can see the behavior of the main resonant peak of the piezoelectric transducer. We can see that there is also an asymptotic increase in the frequency and decreasing in the amplitude. Actually, the behavior of the peaks in terms of frequency was more consistent, and not for the amplitude, just because like a more rigid structures has higher frequency. And usually in the EMI techniques, there are some statistical parameters that are used to assess the damage, and we calculate the root mean square deviation, and we found an asymptotic increase. And then, even though it's not possible to do a direct comparison, we put also the numerical just to see that there was also an increase in the amplitude, in the root mean square deviation. To conclude, we used this technique, and it comes out that it was sensitive to the change of the properties of the interfacial tissue between the implant and the bone. There are some advantages of low cost and sensitivity. Maybe the limits is the repeatability, and also the fact that we have to bond the piezoelectric to the structure. Future study has to be done using a large pool of implants, and also using in vivo samples, and a direct comparison with the commercial available system would be very important. I'd like to thank the US National Science Foundation grant and also University of Palermo for my scholarship. Thank you.